Okay, so we'll get going. So this is day 4 of the transmission line protection topic. So this is going to be our last day of transmission protection, and you've got one more class with me next week on pilot schemes. Or no, I'm sorry, on bus protection schemes. We're talking pilot schemes today, and then you'll move on to whatever the next topic is after me. So. I'm going to jump right in. Quick agenda for today's class. We'll do a quick recap of days 1 through 3, and then we're going to start talking a little bit more about pilot schemes. And pilot schemes are a way to improve some of the protection objectives through adding some communication between the terminals of a transmission line. And there's a whole variety of schemes that are out there. We'll talk about a few of them. Hopefully we'll have some time at the end here. Go over any questions you might have. I guess I do have a question for everyone before we start. Has Paul gotten you guys the homework yet?
We have the OLR file,
okay.
But we don't have any instructions or anything.
Okay, so I think he should be sending that. If he doesn't, let him know. He has it. I sent it to him. I sent him a link to the file. And I'll try to put some time on next Tuesday's call. Then, if you haven't had a chance to start looking at it and going over it, I'll try to dedicate like 15-20 minutes of the Tuesday's class to answering questions, things like that. But if you do have any questions as you get going on it, definitely let me know. You can reach out via email. I'm happy to jump on a call or something like that. I know it sounds like from talking to a couple of you don't have a lot of Aspen experience. I know part of the agenda overall for the class, when Paul reached out about it, did have a few classes on Aspen, but if you haven't had any real world experience working with it, I can give some hints and guidance on that once you try it yourself and come back with a few questions. But a lot of the stuff that you'll need as far as the actual Aspen functions are stuff I very quickly covered at the end of last class. But just come prepared with any questions on Tuesday, and like I said, I'm happy to jump on a call or get back together as needed to go through some other more questions as they come up, or help you out if you have any need any clarification on what's being asked. So all right, so we'll jump right in here. I guess before we do, any questions on stuff we've covered so far? All right, good.
So appreciate if you explain a little bit work on part 4 with Aspen.
Okay. If we have some time at the end, I definitely will. And I can do some more Aspen overview stuff and kind of go over how to do how to model the relays and things like that. If not, I'll plan to cover that on Tuesday with the bus protection one, or I can do a separate quick overview video and have Paul post that as well, so you can just watch it as needed. I just don't want to I don't want to start with that and run out of time on the pilot schemes. So we'll jump in, and if we have some time at the end, I'll spend some more time looking at Aspen specifically. So. All right, so recap of the last few days. We've been talking a lot about these terms, reliability and its balance between dependability and security, selectivity, making sure that we're allowing the right protection to operate and remove the appropriate part of the system that has the problem rather than a larger portion of it. Operate speed, how fast we're able to make a correct decision. Simplicity, how much complexity there is built into the scheme we're applying, and then economics. So We're going to talk a lot more about these again this class. So as I mentioned, pilot schemes add a communications channel between the terminals. So basically the relays are able to share information about what one terminal is seeing versus another terminal. And that allows you to improve some of these objectives. Certainly your operate speed of the scheme, your selectivity, and your reliability are all improved by this, but it's kind of balanced out by the fact that you're applying a more complex scheme because you've got this communication channel to deal with. So you may be sacrificing some simplicity, and certainly sacrificing some economics, because if you have to build a communications channel between your relays, it's a large cost. Oftentimes, there may be some fiber optics or multiplexer networks, things like that already at your station. Maybe you can leverage that instead, but there's still a cost associated with providing this more complex type of scheme. So we talked a little bit about overreaching, underreaching elements, forward and reverse elements. We're going to touch back on this quite a bit on the pilot schemes because many types of schemes rely on directionality and over or underreaching elements as a mechanism for one relay to pass information to the other relay. So one relay might tell the other, I see a fault in my forward overreaching zone, and the other end of the relay would use that information to condition what it does for a trip decision based on what the other relay is seeing. So we'll touch back on these terms throughout this. I just wanted to bring this slide up here. And we largely were talking about step distance schemes for the last couple of classes, and step distance schemes are applied very widely. They have the advantage of simplicity. You're applying fairly simple protective elements that you can set a variety of over and underreaching elements with time delays or instantaneous protection. And locally, just at one terminal, one relay can make a pretty good decision on if a fault is on the line or not. And really, the limitation for that type of scheme comes with the slower operating speed for faults towards the end of the remote terminal, because you're operating in that time-delayed Zone 2 region, and the ability to differentiate between faults towards the ends of the line and faults just past the line. So that overreaching element is going to see faults for parts of the system that are past the line terminal. So you may have a bus fault or a fault past the remote end of the line, and it'll operate for that as well, which means you have to coordinate it with other protection. So those are really the main drawbacks of the scheme. You have to coordinate it, and it can be slow for certain faults. It's high speed for anything in Zone 1, but there's a section of the line towards the end of the zone that is going to operate with a time delay. And in certain cases, that's not acceptable. You have to clear your faults high speed. And when I say high speed, I mean within a few cycles of the fault occurring. So, a fraction of a second. So the delay of a step distance scheme may not be acceptable based on performance requirements of the system. So one of the ways we combat that is by applying what is considered a pilot scheme. So a pilot scheme generally is going to involve some communication between one relay at the one end of the line and the other relay at the other end of the line. And this allows us to achieve high-speed tripping for the entire length of the line, because the two relays are able to share data. And communication requirements are going to vary based on your application, but many of these schemes were designed before we had high bandwidth, fiber optic, multiplexer networks, things like that. Many of them were designed using power line carrier systems and things like that have very limited bandwidth. So many of them really just send a single bit of data, a single piece of information from one terminal to the other terminal that can help it condition and make a more informed trip decision. Some of the more modern schemes, we'll talk about line differential a little bit. are going to require a more robust communication path because you're in that case actually sending a continuous stream of analog current measurements from one terminal to the other. So you're gonna need a more robust channel for some schemes, but a lot of them really just need a single bit of data, which is helpful. So usually we're not just applying a pilot scheme. Oftentimes we will pair this up with some other schemes to provide some backup protection because adding this communication channel adds a failure point. What happens if your fiber optics break? What happens if your transmitter or receiver fails? You still need protection, kind of backup protection in that case, and you're going to want to monitor it to understand what happens. So we've got really two types of schemes when we talk about pilot schemes. The first is a directional comparison scheme. And this is really leveraging the directionality that the relays can tell. And basically, it's one terminal saying, hey, the fault is in front of me, or the fault is behind me. And the other relay using that information along with the directionality of elements local to the remote end to make a trip decision. So we've got a variety of these. The couple main types are permissive schemes and directional comparison schemes, or blocking schemes. But there are some direct tripping schemes as well. So, and we'll go through an example of a few of these. But here's some of the terms you might hear. Permissive overreaching transfer trip scheme, it's a POT scheme. Permissive underreaching transfer trip scheme, or a PUT scheme. Directional comparison blocking, or DCB. Directional comparison unblocking, DCUB. Or direct underreaching transfer trip, or a DUT scheme. So these names and acronyms are descriptive of how the scheme, what information the scheme is sending, and what action it's doing for the remote terminal. And we'll take a look at those in a little bit. The other type of scheme we have is a differential scheme. So there's a whole suite of modern line current differential relays out there. Those are the ones that are sending a continuous data stream of current measurements from one terminal to the other, time synchronized, and provide a differential calculation for the other end. But there's also some older schemes that use telephone wires and things like that, this pilot wire scheme. Generally, we only see these when we're removing them and replacing with a modern scheme, but there are other types of line differential applications out there. That sounds like this. Said someone join. Okay, we got somebody else join in. Okay. All right. So, as I mentioned, you got to have a communications channel to send this data. So you need some mechanism to allow the relays at a relay at one terminal to talk to a relay at the other terminal and send that bit of data or the stream of data. So there's a few different types of channels that are common. We've got least line audio tone, and this is digital or analog, though analog's pretty much going away. I don't think those frequencies are available anymore. So fairly uncommon, but we do see it occasionally these days. Power line carrier uses the conductors of the transmission line to send information from one terminal to the other. And it's a higher frequency signal kind of superimposed on top of the 60 hertz and then received at the remote end. So this is a very common and popular choice, for the last 50 plus years, because the communication medium from one end to the other is already there. You've got the conductors. It's just a matter of providing something to couple that signal to the one or more of the phase conductors of the transmission system. Much more common today is direct fiber. So this would be using those OPGW optical ground wire that we mentioned in the first class, or a just dedicated ADSS type fiber cable between the two terminals. Basically, you have a fiber optic connection from one relay to another relay directly. We can also use multiplexer networks. So a lot of utilities have a multiplexer network that's built along a fiber backbone, but basically provides a bunch of rings that share data, a variety of types across the network. And this could be SCADA data, it could be telephone data, it could be relay communication data, but it's multiplexed over a specially designed network. And then lastly, microwave. Microwave is probably less common because it's very expensive, but is still another viable option to install microwave towers with transmitters and receivers pointing at each other over the length of the length between the two terminals. So the carrier schemes, we got a couple types: on-off, on frequency shift keyed carrier. I won't go into a lot of detail on those, just some details on what the communications channels might look like. One key thing on these communications channels is they have to be really high reliability. So these need to be available almost all the time. If they fail, we need to know about it so we can we can send somebody out to fix it. So they're really high reliability, even though they're not high data throughput. They do need to be very high reliability and high uptime for the communications channels. Because anytime it goes off, we lose our protection, or that piece of the protection. So I wanted to cover a couple operation examples for pilot schemes. The first is going to be our permissive overreaching transfer trip scheme. So each of the relays on either end use a overreaching forward-looking element, and that's shown by these arrows up here. RO is the relay overreaching element. So the one pointing from kind of this arrow pointing from this bus out past that one is kind of a representation of the overreaching protection applied at the relay associated with circuit breaker 1, so this relay. And then the top line up here pointing in the other direction is a representation of the relay associated with circuit breaker 2 here. So in between these two relays, we've got the protected lines. This is our zone of protection. The thing we want to operate for is anything in the line section. What we don't want this scheme to operate for is anything outside of the line protection. And that's going back to the security and dependability and selectivity criteria. So the way the scheme works is if one relay sees a fault in this forward overreaching zone, that means it knows that the fault is on the line, and it sends that information to the other end. So the relay for a fault on the line, the relay at breaker 1 sees the fault and sends a signal to the remote end saying, hey, I see a fault. And then the receiving relay at circuit breaker 2 will take that and say, hey, do I also see the fault? And by process of elimination, if they both see the fault, that means the fault's on the line, and the scheme should operate. And if they both don't see the fault, they will not operate. So I think, okay, yeah, all right, good. I did set that up right. I've got an example here. It's an in-section fault example. So this is a fault on the protected line. First thing that happened is a fault occurs. So we've got the fault here shown midway down this line. Okay. The local relay elements assert. So because this fault is within this overreaching zone on from both relays, both of the overreaching forward elements assert. The permissive signals are transmitted and received as appropriate. So the transmitter on the circuit breaker 2 side has seen a fault, so it sends a signal to the receiver on the other end. Similarly, the transmitter from circuit breaker 1 sends a signal to the receiver on the other end. The logic is processed. So even though we saw the fault within these overreaching zones, the relay isn't making a trip decision on its own. It's waiting for this other piece of information to come through. And basically, the AND gate here is saying that the relay at circuit breaker 2 sees a fault in front of it, and the relay at circuit breaker 1 from the other terminal also sees a fault in front of it. In this case, the AND gate is satisfied, and we move to trip the make a trip decision, and we trip the breaker at either terminal. When that happens, the fault's clear, the line's de-energized, and the scheme has tripped. So, typically this type of scheme is going to operate fairly quickly. The only delay we're really going to have is the delay for sending the bit of data that is this transmit signal from one end to the other. So it can operate very quickly, and it can make a very very good decision, reliable decision on if the fault is within the protected line or not. The reason this is called a permissive scheme is because basically the signal that we're transmitting from one terminal to the other is giving the other terminal permission to trip if it also sees a fault. And in this case, it did. So that's kind of where this name comes from. Permissive, meaning we're giving the remote terminal permission to trip if it decides to with the other data that it has. Overreaching, because it's giving permission based on an overreaching element. And that's a transfer trip scheme because we're transferring data to inform the trip. That's just what we call basically all of these types of schemes is a transfer trip of some sort. So if we look at the same scheme, but we look at an out of section example, we'll see how we prevent tripping for a fault past the protective zone. So we'll start the same way. The fault's going to occur, but in this case, our fault is happening at the remote bus here, somewhere just past the remote bus on a line or something like that. The local relay element assert as necessary. So in this case, the relay at circuit breaker 1 sees the fault in its overreaching zone, but the relay at circuit breaker 2 does not, because the fault is behind it rather than in front of it, kind of getting back to that forward and reverse directionality. So the overreaching element here does not assert and is not sending a permissive signal. So our same thing in both terminals, permissive signals are transmitted and received as appropriate. So in this case, because only the relay at the circuit breaker 1 location sees the fault, it is the only one that is transmitting a permissive signal. And then our logic is processed at either terminal. So the receiver has received this, and we're logically asserting the fact that we've received it in the POTT scheme logic. But because on breaker 1, this relay sees the fault but has not received a permissive, the AND gate here is not satisfied and no trip is made. And on the location of circuit breaker 2, we've received permissive, but the local element does not see a fault in front of it. So in this case, the AND gate is also not satisfied. So no trip command is made here either. So, sorry, my slides are moving ahead of me here. So in this case, we have an out-of-section fault example, and this scheme is just not going to operate for that out-of-section fault at all because we've added this additional complexity and this additional logic and additional information about what's going on at the remote terminal. So, this fault isn't going to just stay there forever. There'll be other protection that would be the primary protection to clear this fault. So this would clear from some other system, or potentially you'd have a step distance scheme at circuit breaker 1's relay in parallel with this POTT scheme that would see that fault and operate for it. But the POTT scheme itself is not going to operate for that fault, and the fault will eventually clear through some other means. Any questions on the POTT scheme? I'm going to move over to, I think the next one's a directional comparison blocking scheme.
Can we go with the example and with the figure on the example?
But as far as I mean, these are the two examples I have, is the in section or out of section fault example. Is there one you had a specific question on?
Yeah, that's right. Thank you.
Okay. Okay, looks like I have it. Let me see what other schemes I have here. UTT scheme. Let me just see this real quick. Okay, I did provide it. All right. Okay, sorry. I just wanted to, I didn't have a chance to review my slides ahead of this, so I couldn't remember what all the other schemes I applied here. So another variation of this scheme is a permissive underreaching transfer trip scheme. And it gives the same basic concept that we're providing permission from the remote terminal to trip based on what the local terminal sees for a fault. So in this scheme, we've got two elements at each end. We've got a overreaching element and an underreaching element. And this scheme would typically be applied in parallel with a step distance scheme, because we're going to rely on the step distance scheme for clearing some of our faults. So we'll take a look at a in-section example here. This is a less common scheme. I have seen this scheme applied before, but I'd say the POTT scheme is much more common, primarily because of the additional complexity that comes with this permissive underreaching scheme. So we'll start the same way. We've got a fault. In this case, it's a fault near the terminal 2 of the transmission line. Each local relay is going to assert and make a decision if this fault is within its protective zone. So the relay at circuit breaker 1 is going to assert in its overreaching zone, but not assert in its underreaching zone. So this RU here is its underreaching element. Because the fault is past the end of that underreaching element's reach. The relay at circuit breaker 2 is going to assert both on the underreaching element and on the overreaching element. And you can see the logic here. The underreaching element is directly going to trip the circuit breaker. So this is basically your zone 1 of your step distance scheme operating instantaneously. So this is one of the advantages of this scheme, is for a close-in fault, one terminal is going to clear and trip slightly faster, maybe a couple cycles faster than the remote terminal. So in this case, we've already made a trip decision and the trip is asserted. We send a permissive signal from, at the same time as the trip is being asserted, we are sending a permissive signal to the remote end. This is sending permission, allowing the remote end to trip on its overreaching element. And then the logic is processed on the circuit breaker 1 side and on the other side, though this AND gate here doesn't get satisfied because there's no permissive signal received. But there isn't needed one, because you've already directly made a trip decision based on your underreaching element. At circuit breaker 1's relay, this AND gate becomes satisfied. It passes through this OR gate, and a trip decision is made there. And both terminals clear the fault as expected. So this is kind of a variation halfway between a step distance scheme and a POTT scheme, where it's using both the over and under reaching elements, but leveraging that permissive approach to a pilot scheme by sharing that piece of information. So one other type of scheme I will go over, I think it's the last one that I'm going to cover other than line differential, is a directional comparison blocking scheme. So this is a little bit different than the two permissive schemes we've looked at, where the information that we're sending from one terminal to the other is not permission saying, hey, I see a fault on the line. It's saying, I see a fault behind me, which means the remote terminal shouldn't trip, because if the fault is behind the local terminal, that means it's not on the line. One relay knows it's not, the fault isn't on the line, and is sharing that information with the other terminal via a blocking signal. And this type of scheme is more commonly applied when you have a communications channel that may be interrupted by a fault on the transmission line. So, for example, the power line carrier scheme that I briefly touched on, that uses the conductors of the transmission line as its communication medium. This would be a very typical scheme to apply on a carrier type channel, because the only time you're sending a signal is when the fault is not on the line. If the fault is on the line, it may interrupt the signal, so you can't apply a POTT scheme directly in that manner. So I'll run through an in-section fault example here, and then I think I've got a out-of-section fault example as well. So we'll start the same way. We've got a fault on our protected line. Each relay asserts the appropriate elements. In this case, because the fault is on the line, it's in the overreaching zone, forward overreaching zone for each line. And the reverse looking zone, this blocking zone, is not asserted because it does not see the fault. So the local relay elements assert. The blocking coordination timer starts timing. So at this point, you can't make a trip decision because you've got to wait some time to receive a block from the other terminal. So even if the block isn't coming, you still have to give it an opportunity to be received before you make your trip decision. So we program a short time delay to this, and it might just be a few cycles or a couple cycles, basically long enough for when a block is sent for it to make it from one relay through the communications medium to the other relay. So at this point, this AND gate, because the input is inverted into the AND gate, this timer starts timing, and this timer starts timing. So these TL1 blocking coordination timers start timing, but they haven't timed out yet. Blocking signals are transmitted and received as appropriate. In this case, we aren't transmitting anything because the blocking zones, the reverse looking elements, are not seeing the fault behind them. So neither terminal is sending a block to the other end. And because the block is never received, eventually this TL1 blocking coordination timer times out. And when it does, it trips the circuit breakers. So a trip decision is made at both terminals because neither terminal received a blocking signal. So we'll go through another similar out-of-section fault example. So if we have this same fault behind this relay, so behind the CB2 relay, the fault occurs, the relay's currents and voltages change, and makes a decision based on that, which elements assert. And you can see that at circuit breaker 1, we've got the forward-looking overreaching zone asserts because it sees this fault even though it's past the end of the line. But at circuit breaker 2's relay, the blocking signal asserts because the fault is behind that relay based on the location of the CTs. So the blocking coordination timer starts timing at terminal 1. So you can see this AND gate is receiving an overreaching zone and it's not receiving a block. So the TL1 timer starts timing. At terminal 2, that timer does not, because you haven't received this overreaching element, so you're not going to, this AND gate isn't satisfied and the timer doesn't start timing. But a blocking signal is sent. So a blocking signal is sent from circuit breaker 2 relay over to the circuit breaker 1 relay based on the assertion of this reverse looking element. When this is received, now the input to this inverted input to the AND gate is now a logical 1, which defeats the AND gate because you've got it's receiving a logical 1 from the overreaching element and a logical 1 from the receiver, and it needs a 1 and a 0. So the AND gate is then defeated, it's no longer asserted, and the timer drops out. So the TL1 coordination timer drops out. And as is expected, because for an out-of-section fault, no trip decision is made because the fault is out of section. So this is kind of very similar to what we did on the POTT scheme, but we are applying this kind of in reverse logic, rather than one terminal saying, yes, the fault is on the line and sending permissive signal to the other. We are sending information that, no, the fault is not on the line. I know it's behind me, so don't trip. So it's, again, sharing a single piece of information between the two lines allows you to do this high speed and very more selective type of scheme. All right, so I've got one more. I think this is the last one. I'm running out of slides here. So I've got one more example here of another type of pilot scheme. It's a direct underreaching transfer trip scheme. Direct tripping schemes don't rely on any conditioning from the remote terminal. So you directly send a trip from one terminal to the other based on information that you have at the local terminal. So it's not permissive, it's not blocking, it's just directly allowing one relay to send a signal to trip the breaker at the remote terminal. So I'll go through an in-section fault example here. This one is using just underreaching elements. So you can see we've got an underreaching element here, and hence the direct underreaching transfer trip scheme. And so you don't have any elements that are looking and seeing faults for the entirety of the line. First thing happens is the fault occurs. In this case, it's another fault past the end of this underreaching element near the breaker 2 terminal of the transmission line. And as we have on other examples, well, the first thing we do is, we see what elements operate for this fault. In this case, the fault is past the reach of the remote of the underreaching element at the relay associated with circuit breaker 1, and is within the underreaching element of circuit breaker 2. So the element associated with circuit breaker 2 asserts. That logically goes through this OR gate and trips the breaker at circuit breaker 2. And at the same time, it sends a signal down to the transmitter for the scheme. So circuit breaker 2 is tripped directly based on the assertion of the underreaching element. We're able to trip it directly instantaneously because we know it's on the transmission line, because it's an underreaching element. The transfer trip signals are transmitted and received as appropriate. In this case, we are sending a signal from terminal of circuit breaker 2, the relay, to the receiver at circuit breaker 1. When that's received, it directly trips the circuit breaker at circuit breaker 1, and the trip decision is made, and both circuit breakers have operated to clear the fault. So this is the last of the directional comparison type transfer trip schemes. that I'm going to cover, and went through a whole bunch of information there. And I'm hoping the kind of graphical representation and examples have helped kind of show, at least in concept, what we do with these schemes. Any questions on these? I do have a couple slides on line differential as well. And a couple things to wrap up.
So does Aspen help us to solve this kind of problem with regard to line correlation?
Yeah. So where you would use Aspen in this case is each of these schemes relies on some type of overreaching or underreaching, forward or reverse protective elements. So where we'd use Aspen on this is either applying fault analysis to set the elements, using the line impedance data, like we're doing in the homework example and the example I showed in the last class. That is how we'd use Aspen in this. Would be basically to figure out how to set these elements to over or under reach the terminals. And then you can use it to validate the fact that you've got the appropriate amount of overreaching and underreaching. And these overreaching and underreaching elements, typically they're applied as distance elements, though some schemes also use directional overcurrent elements as well in a similar way that you may add a directional overcurrent element to the scheme. So it might actually be more than one overreaching element or underreaching element. You'd be typically applying phase and ground protection for each of these elements as well. So that's really where Aspen comes in for these types of schemes is selecting and then validating the over and under reaching element settings and their reaches. Though you can actually model these schemes in Aspen. So I showed briefly last class how to, how we can see the Mo characteristics of the elements and see the operation of the elements. You can take that a step further and actually model the elements and then model the logic within these schemes as well, so that you could run a fault and say, does my POTT scheme assert for this fault, or does my direct underreaching transfer trip scheme assert? So you can model this protection, this logic and these schemes in Aspen, though I've yet to find a utility who does that. Usually it's just very easy to say, oh, well, we've applied a POTT scheme, that's going to operate instantaneously, and then be done with it and just say that's good enough. So any other questions?
No, thank you, sir.
Okay. Anyone else?
No, thank you.
All right, great. So get myself moving here. The last type of protection I wanted to talk about, because it's becoming much more widely applied as utilities have, ever increasing communications capabilities. There's a lot of utilities that every time they put up a new transmission line or reconductor a new transmission line or do work on a new transmission line or an existing transmission line, they are applying, they're adding fiber optics to it, either as OPGW or ADSS, which is just a strict fiber optic cable that you can apply on this through transmission lines. So, when you have a robust communications channel available, this is a very common scheme because it has a lot of advantages. So all the other schemes we talked about, we're sending a single bit of information from each terminal. We're saying, yes, the fault's in front of me. I give you permission to trip if you also see a fault, or it's sending a blocking signal that one terminal is telling the other the fault is behind me, so I know it's not on the line, so don't trip. And lastly, the direct trip signal that we're sending a single bit of information that says, hey, I know the fault's on the line. it's in my under reaching it zone, just trip your breaker. Don't even check, just trip it directly. So, those schemes goes a really long way, but as you have a more robust communication scheme like fiber optics, we're able to do a little bit more and, maybe, sacrifice a little bit of more complexity to gain a little bit more speed, a little bit more security and dependability, and maybe provide a little bit better, more of a robust protection package. Um, and that's where line current differential comes in. So line current differential typically requires, fiber optics or a multiplex or some kind of a higher bandwidth communications channel to send information. And the information it's sending is a stream of measured currents from one terminal to the other terminal. So differential principle in general, if I don't know if anyone has covered that yet, is basically Kirchhoff's current law. The current into the line has to equal the current out of the line. If they don't, there's some other place for the current to go, and that would be your fault. So you would have a fault condition. The current's probably coming in on both terminals rather than the current flowing through the line. So differential principle is a pretty powerful one. We use it on a lot of different types of equipment. And lines are one of them. It's just a little bit more complicated where the current measurements aren't all locally at one substation. So a few things with line current differential to look out for. Basically, we need to have that robust communications channel. We're going to send the current measurements from one terminal to the other terminal, and the receiving terminal will synchronize the measurements from its relay with the measurements it's receiving, because there's going to be some amount of time delay. So you've got to synchronize timing, and it's going to compare those two quantities, basically add them together, and they should sum to zero. If they don't, there's probably a problem, and that's what it uses. It uses that differential current, or the summation of the terminal currents per phase as its operate quantity. There's a few things to look out for this. A lot of schemes you could, though it's really not great practice, have different relay types at either terminal. You could have electromechanical relays at one terminal and Schweitzer or some modern microprocessor-based relay at the other terminal. And you could reasonably still make a POTT or DCB, one of those types of schemes work. This type of scheme, you really have to have the same equipment at both ends. It has to be the same relay type, it has to be the same firmware, it has to have the same communications equipment associated with it. So there's a little bit more to coordinate there, as well as you have to make sure that your communications link between the two relays is, highly reliable and is compatible with the type of relay you're buying, because there's a lot of different options out there. Many of the line differential relays come with a bunch of additional features. So there's things in there to compensate for line charging currents due to the capacitance of the transmission line, which those currents are present even when the one terminal of the relay or the line is opened. Compensate for tap transformers and other things connected in the middle of the line. And some mechanism to synchronize those local and remote measurements. So generally, as I mentioned, we're talking about direct fiber, though you can do it over a multiplexer as well. Usually those are fiber optic based as well. And there's a couple different communications methods that you can use with a serial or interface type, serial or Ethernet interface type application. So line differential is a huge topic all on its own. One thing to point out is that there is all these figures that I've had in these past slides are from C37.113, the 2015 version. They have a new version that's out that's even better. I haven't updated the slides for it yet. But this is a IEEE guide for transmission line protection. There's also a new guide coming out, and I don't remember what the number is, that's dedicated to line current differential. It's like a 100-page document going over all the considerations, all sorts of great stuff about that. So I encourage you, if you're, starting your career and want to learn more about any protection topic, the IEEE standards, the C37 series, we've got a guide for pretty much every type of major equipment. Transmission lines has a ton of information in it about all of these schemes. So great place to look if you want to learn more. So here's a rough comparison of these schemes, kind of looking at a few of these main protection system objectives. So this is just my own thoughts on it, but I thought like a rating system would be a great way to kind of compare these schemes and what some considerations may be. There's no one scheme that is truly the best in every scenario. There's going to be reasons why in some applications you might want to use a DCB scheme over a POTT scheme. There might be some considerations when you really want to use a PUTT scheme over a POT scheme. So this is just my own thoughts on it. This isn't any kind of official thing that people should go, take as the full truth here. But, if you look at the schemes here, you can see their operate speed for these schemes is all fairly quick. We're talking, 1 to 2 electrical cycles. The DCB scheme being maybe the outlier here, or in DCUB scheme, because we've got to wait for that blocking, or in the case of DCUB, an unblocking scheme signal to be received. And we have that coordination timer that, makes it so we have to wait a little while before we trip, but still we're going to make a trip decision in, 2 to 3 cycles, electrical cycles. So very quick. Your channel requirements, most of them here, you can see we have a single bit transmitted and received we're sending. And then we got some considerations in here. POTT and PUTT schemes, they can't use a type of communication medium that could be interrupted by the fault itself, or you're not going to get that permissive signal out there. The blocking signal, the blocking schemes, non-blocking schemes, the DCB and DCUB, you need that same 1 bit of information, but they are set up in a way that you can lose communication during the fault, and this scheme will still be able to take that. And that's why we typically apply these if we're using a carrier scheme, because the loss of the communications channel shouldn't matter, because we're sending a signal that's indicating that the fault is out of section. DCUB is a little bit more complicated. We don't see this one very often, but it is applied occasionally, where we're actually monitoring this health of the communication channel. If we lose the communications channel, we allow it to trip high speed, even if we haven't received a permissive signal or an unblocked signal. Your DUTT scheme is, again, it has to be uninterrupted during the fault. And then 87L, you need a much more robust, you're talking about 64 kbps type channel. And then if we start looking at security, dependability, and simplicity, this is really where you can start comparing these schemes. So your POTT scheme, it does pretty well with security, because you're relying on that permissive signal, and you have to have a local trip. the dependability is also pretty good, and your simplicity is pretty good because it's not that complex. You don't have a lot of extra logic. DCB is maybe a little less secure because you're making a decision based on a blocking signal. If the blocking signal doesn't get through for some reason, you could trip or not. You could block a trip when you or you could not block for a trip that you want to block for. But it's highly dependable because if your communication channel just completely fails, it's going to trip for a fault on the line. We didn't really touch on DCUB, but it's a very complex scheme, so that's why we don't see it applied much, and you don't get a lot of advantage over a DCB or a POTT scheme, so those are much more common. And then lastly, we've got the line differential scheme here, which is very secure because we're giving each relay a lot of information about what's going on the system, not just a blocking or permissive signal, but also we're also giving it the actual measurements so that it can use those to make a more informed decision. But that comes at the sacrifice of simplicity because we're applying a much more complex communication-based scheme. And there's a lot more things we have to consider as protection engineers. So this is just kind of my thoughts on some of the advantages and disadvantages of the schemes. In general, if applied properly, every one of these schemes can be applied with very good security and dependability. Just because one has 3 stars, the other one has 4 or 2, doesn't mean that it's not a dependable scheme. These are all very robust schemes, and they're very well proven in industry. So a couple general application considerations for pilot schemes. Often we'll see them applied with cutoff switches. These would be switches that will allow you to turn on and off your pilot scheme in case you need to do maintenance in the communications channel, or you might need to do some other type of work that would make it so that you need to turn the scheme off. That's why typically we also provide the backup protection for these schemes. Because when it's turned off, you're not going to have any protection if you don't apply a step distance scheme or a directional ground overcurrent scheme, something like that. Generally, the communications channels need to be continuously monitored. So we need to understand and know an alarm if the communication channel fails. And that way they can send personnel out to identify the problem and correct it. And this is important not only just for good practice to understand if your scheme is operating properly or not, but it also impacts some of our NERC compliance requirements for maintenance testing intervals. So if a scheme is continuously monitored, it has to be tested for maintenance tested less frequently. There's also redundancy needs. So oftentimes we're applying multiple schemes. So we apply maybe a system 1 scheme and a system 2 scheme. They're redundant, so they are intended to operate in a similar manner. We need to make sure the communication paths and other pieces of the scheme don't create a single point of failure. So you wouldn't, for instance, want to apply both of your schemes in one fiber optic cable, because what happens if the cable fails? If there's some failure mode within the cable that impacts both schemes, you lose your protection on both. You really have some other things you got to think about when you're deciding which one of these pilot channels to use. You might want to consider, how the relay is going to operate, what those elements are going to look like, how fast you want it to work, how long your line is. So there's going to be a lot of things you want to look at and consider at the early on in the scoping of a project to decide what scheme to use, one versus another. Utilities often have either philosophy on when to use each scheme, and that's kind of decision. It's you follow their process and make a decision based on that. We also might run into these with multi-terminal lines. So we've primarily been talking about two-terminal transmission lines. We've got transmission line between station 1 and station 2. There are also cases where you have multiple terminals. So if you have a tap point midway down your transmission line, you can then bring that out to another station and have a 3-terminal line. It'll have different power flows through each of the segments up to the tap point, and also different fault currents going on. But most of these pilot schemes, and the step distance scheme for that matter, can be applied on a multi-terminal line. You've just got to look at things in a lot more detail, because it's a little less obvious to be able to tell, is this overreaching element going to overreach all remote terminals in all cases? So there's a little bit more analysis required, and then there's some more logic, because you might have to receive permissive signals from both terminals, or you might be sending your blocking signal to both terminals, things like that. Another key thing to note is oftentimes, we've got this communication channel for a relay. We're using a single bit for our pilot channel. We may be using other bits within that same communications medium for other protective schemes. So breaker failure transfer trip is a separate scheme, but it may borrow some of the spare available bits within the communication medium that we're using for our pilot scheme. And then pilot schemes often involve a lot of relays or IEDs that need to be specified, designed, set to make the scheme work correctly. So, often this might include carrier sets, tone sets, multiplexers, fiber optics, and you might need to know what type of fiber it is. Is it single mode? Is it multi-mode? How is it spliced? How do you document, which fiber on one end connects up to the other fiber on the other end? And you might order relays with communication ports that need to be changed to align with the type of communications you have. So you might have to use port adapters or specialized cables to connect it up in a way that allows that communication channel to work. So, pilot schemes are, again, it's a balance of the advantages you get of increased speed and increased selectivity, improved reliability overall, but it comes at the sacrifice of complexity, because you're having a lot more components you have to deal with, specify, and you have a lot more things you got to get right for the scheme to work properly, and more failure points within there. So that complexity or simplicity piece comes into play as one of the objectives there. And it's like anything, it's a balancing act between all of those. So I put some links here to some additional reading if you're interested and want to learn more about transmission lines. This C37-113, like I mentioned, there's now a 2025 version. It might be a 2024 version that's updated and improved. It's worth checking out if you are starting a career as a protection engineer. These guides are great. They're intended for folks just learning and trying to understand how to properly apply these types of schemes. So definitely worth checking out. I've got a couple other references here. This transmission line settings calculation beyond the cookbook paper by Mike Thompson and Dan Heidfeld is a really great intro to transmission line settings. There's a follow-up part 2 on this that goes into some more details to some other stuff. And a couple other another paper, and then a book here. This Protective Relay Principles and Applications book is a really great resource for any protection engineer. So that brings us to the end of the transmission line section. We covered a lot of ground and talked about a lot of stuff. I probably could do another, half a dozen classes on transmission lines here if we had more time. But hopefully you've gotten a decent view of what transmission line protection is all about, some of the types of schemes will apply, considerations for meeting all of those protection objectives, and hopefully give you at least a little bit of background to understand a little bit better about how these schemes work. So with that, we do have about 5 minutes left. Do we have any questions on any of the stuff I've covered over the last 4 days? Don't have a ton of time, but I can certainly, if there's any specific questions about Aspen, I could bring that up and answer any if folks have started using the software at all.
The question, the part 4 of the the homework, if is it possible a little bit, please explain how to go with the Aspen. Sure.
Yeah, just a second. Let me see if I can open that up. I just got to remember which one part 4 was. Okay. Part 3, part 4. Okay. Okay. So yeah, I can give a little bit more information on that. Let me open up. Actually, I'll open up from over here. Make sure I get the right one. Okay. So we are working on relay settings for the relay at this Fieldale terminal. Parts 1 through 3 have you calculate the set points for your phase and ground distance protection and evaluate the loadability of your phase protection. So you should come out of that, and I think I had a place listed in there. Let me see back on the assignment here. Yeah, so we had these settings here. Zone 1 ground reach, the zone 1 ground delay, zone 2 ground reach, and the zone 2 ground delay, and then these K factors for the zero sequence compensation factor. I mean, it's similar up here as kind of the result or the answers that you'd get for your settings for the phase elements. So we've got the MO phase, zone 1 MO phase reach and delay, and the zone 2 reach and delay. So once you calculate those, the idea is that we'll model that protection. So rather than have to have you figure out how to go in and find the right relay model and set everything up, I created a relay model here. And if we look at the phase version, you'll see there's no MO characteristics on here. It's just the transmission line, and doesn't have anything applied. So if you open up, you can either open up this way through look at the characteristic and then double click on the box up there, or you can double click on the relay group here and find the element, and then click get info, and this will bring up that same window that is this is the relay model window. A few things here. You can see it's a type SEL 421P. So the Schweitzer 421 is the relay type we're setting. P indicates it's a phase distance relay. You can see it's up here. So it also says distance phase relay, and it says it's on this terminal. That's telling you where it's located. And has this name F-C for Fieldale Claytor line 21P, meaning it's a distance phase relay. So all of the elements that we are, the 2 elements we're applying in zone 1 and zone 2 would get added in here. And there's a handful of other information that we're going to need to know to have Aspen understand how to model this relay. So I filled in some of it for you. The PT ratio and the CT ratio are in here. They should match what's in the homework assignment. If not, you can change them if you want to, or if you just feel like changing the CT ratio, that's fine too. I norm is the nominal current, so it's a 5 amp secondary CT. So it's saying this is stepping it from 1200 to 5, which the ratio to 1 is 240. You could also express this in here as 1200 to 5, and that will work with the software as well if that's your preferred way to do it. Usually I just put the ratio to 1. CT polarity is reversed. This is no, so this is a typically connected relay, meaning that it's CT is looking onto the line and that impacts your directionality, so you don't have to change this setting. The stuff that you do have to change is you're going to need to specify the zone 1, or the positive sequence impedance magnitude and angle. So in calculating your distance elements, you will need to calculate your secondary impedance values, because the ones in Aspen are in per unit. Those values would go in here. It's a secondary magnitude and angle associated with the line impedance. Advanced settings you do not need to mess with. That enables a bunch of other things that we're not going to worry about. E21P says how many MO phase distance elements are we going to enable? We're enabling 2 for zone 1 and zone 2. E21XP, this would be if you wanted to provide a quadrilateral element, which we do not. And then we've got your settings here. Z1P is your zone 1 reach. Z2P is your zone 2 reach. Z1PD and Z2PD are your delays for those elements. So you would take the settings that you've modified in there or calculated from your question 1, and you'd put these in here, and then you should be able to see that relay characteristic. So for instance, if I put 8 and 10 and 50 cycles as the delays, I can click OK. I can look at the curve. And, maybe it doesn't look very optimized here. It looks like my zone 1's overreaching. So maybe the guess that I made wasn't as good as the answer you'll calculate. But that's what you'll do. You'll also see the relay characteristic isn't in line with the angle of the line. And that's because I did not update these parameters. So maybe this is 5 ohms and 75 instead. You can see that kind of tilts this line back. So the thing we'll be looking for here is making sure you've got these settings applied correctly. And then you can go in here and you can add your load region. And you should be able to get these parameters out of the assignment, and you can show and add your load region on here, and then you can graphically see if you've got a load overreach or not. And none of these values are the answer to the homework, so you can figure it out on your own and see how your settings and your load evaluation look. It's very similar for the ground element. There's a few additional settings in here, but it's a lot of the same stuff. We've got both the positive sequence and zero sequence impedance is important here. So you'll fill both of those out based on your calculations. In question 3, I think it is. And we've got this Z1MG, Z2MG. These are the distance reaches for your ground element, and then the delays are the GD elements down here. And the last thing you'll have to set up to make this operate correctly is going to be the K factor. So you'll calculate that K factor, and you should get a magnitude and angle out of that get applied in these settings. And when you fill that out, you'll then be able to do the same thing. Click Show Curve. You'll be able to see the curve, and you can right-click and copy the graph to your clipboard, or just do a screenshot. And that's what I'm asking for there. It's just a visual representation of the settings you provided. If they look like this and your overreaching element or underreaching element's overreaching and your angles are wrong, it might be a clue to go back and kind of take a look at your application, because it should look very similar to the examples we went over in class. So, any other questions? I know we're a couple minutes over here. Do you want to be respectful of people's time, even though I already went over? Okay, great. Well, I will set aside a few more minutes to go over any other questions folks have on the assignment. next Tuesday. I was thinking a week from next Tuesday as a due date for it. That'll give you, well, I guess Paul has to post the actual assignment, so maybe we'll wait and see when he posts it, and then give you a week or two after that to get the work done. So we can circle back on that on Tuesday. But I'm pretty flexible as far as timing. So, great. So, any other last questions before we wrap up for the day?
Thank you.
Okay, great. Well, I really appreciate everybody joining in today and hanging on for a couple extra minutes. I will get the recording up to out to Paul, who will get it posted for you here sometime shortly. So, thanks again.
Thank you.
Thanks,
Have a good
Brian.
one.
Have a good one.
Thank you.